Greetings and salutations, magical chemists. Let's talk about the glories of equilibrium. In chemistry, we often like to pretend that reactions run in one direction, from reactants to products, but that's not usually the case. In fact, many chemical reactions are at equilibrium, which we indicate by double-headed arrows. In a state of equilibrium, both reactants and products are going to be present. It's important to officially define equilibrium. And when a system is in a state of chemical equilibrium, the rate of the forward and the backward reactions are exactly equal. This means the forward and backward reactions never actually stop. It's important to recognize that the concentrations of reactants and products at equilibrium are not usually the same. However, because the rates are equal, it makes it look on a macroscopic level that the amounts are unchanging, so the concentrations of the reactants and products are constant. There are two different graphs we can consider when we're trying to determine if something has reached equilibrium. The first one is considering rate versus time of the forward reaction and the backwards reaction. Notice at the very beginning of the reaction, if you're starting only with reactants, the forward rate, the rate at which reactants turn into products, is pretty fast, but it slows down over time as you use up some of those reactants. Similarly, the backward rate starts at 0, right? You don't have any products. But as reactions are turned into products, products start turning back into reactants. And you reach equilibrium when they hit equal rates. Another graph that you will see is when you're actually looking at the amount of reactants, usually their concentration. Well, again, we're starting at the beginning with all reactants, and of course that amount is going to go down. You're starting at the beginning with no products, and that amount is going to go up. But notice when you hit equilibrium, the amount stays constant. Now let's take a look at how we can be quantitative in our discussion of equilibrium. To do so, we need to learn about the equilibrium constant K, sometimes called the law of mass action. It just relates the concentration of reactants and products at equilibrium at a given temperature. For a general reaction where A plus B makes C plus D, K is written in this form. Basically, you're taking the concentration of each product on the top and you're raising it to an exponent of its coefficient from the balanced chemical equation. And then you do the same thing on the bottom, but on the bottom, of course, are going to be your reactants. And for each reactant, you're also raising those to the power of their stoichiometric coefficient. Of course, the only way to do this is to have a balanced equation. It is very important to note pure solids and pure liquids, basically anything with a little parentheses of S or L next to it, are not included in an equilibrium constant expression. And good news, there are no units on the equilibrium constant K. All right, let's go ahead and try writing some equilibrium constant expressions. If you're feeling brave, you should go ahead and try number 1, and when you're ready to check your answer, unpause the video. The first thing to notice here is that there is a liquid in this reaction, and that will not be included in your equilibrium constant expression. But everything else is a gas. Gases totally count. So let's write our K expression. K is defined as products over reactants. And you don't have to write that, but I am doing it just to remind you. So remember that we're taking the concentration of our products. Well, the only product left is carbon dioxide. To show the concentration, I put CO2 in square brackets. And then, well, it has a coefficient of 6, so that means I raise it to the power of 6. And then on the bottom, I do that with my 2 reactants. Since C6H12 had a stoichiometric coefficient of 1, we don't actually write anything because, 1 is implied. But that's it. That's your equilibrium constant expression for K. All right, if you didn't try that one, you're definitely going to try this one. And when you're ready to check the answer, unpause the video. Did you realize there was a solid that we didn't have to include? And there you have it. Concentration of products divided by the concentration of reactants. Okay, let's try a problem with some actual numbers in it. So for number 3, on the top of the next page, we are given another reaction, and we're actually given the values of the concentrations. So the first step, of course, write your K expression. So you try that, and when you're ready to check your answer, unpause the video. By the way, When you are writing your equilibrium constant expression in terms of concentration, all these square bracket things, sometimes we actually call this a Kc value. Oops, that's a highlighter, a Kc value. So they could call it K or Kc, it means the same thing. All right, so the next part, they want us to solve for K, which means find out the numerical value. Well, that's easy. I'm just going to take the values of the concentrations that they gave me and plug them in to my K expression. And then you just plug it into your handy-dandy calculator. Yay for free response. Now, funny story, you probably noticed that's a pretty tiny number, right? Well, that actually tells you something about the reaction. So there's an expression, there's a phrase we like to say. We say, is it forward favored or reverse favored? Basically means if it's forward favored, does it have more products? Or if it's reverse favored, it would have more reactants. Well, look at the concentrations. You've got lots of reactants on the bottom. You really don't have very many products on the top, right? And that's why you have such a tiny number. So in this case, the reverse reaction is favored because you have such a tiny value for K, showing you have very few products and lots of reactants. So let's go ahead and talk a little bit more about the important information you can gain by looking at the numerical value for K. Now the crazy thing is, it doesn't matter how it starts. At a given temperature, a reaction will reach equilibrium with the same ratio of products to reactants every time. But you notice we keep saying at a given temperature? That's because equilibrium is temperature dependent. If you change the temperature, you will change the ratio of products to reactants. Now let's talk about what information the equilibrium constant tells you. Like, what does it actually mean? Well, if your value for K is greater than 1, then that means product formation is favored. Relative to the amount of reactants, you've got lots of products. However, if K is less than 1, reactant formation is favored. It means you've got a lot more reactants than products at equilibrium. You can even represent this graphically. I know you're excited. So if you're graphing concentration versus time, notice both the concentration of products and reactants has become constant. But in this particular example, you've got lots more products. So this is an example of a product-favored reaction where K is greater than 1. And the opposite graph is showing you a reactant-favored reaction because at equilibrium, you've got more reactants than products. So from this graph alone, you could tell that K is less than 1. Now, if K is right about equal to 1, well, then the formation of reactants and products are about equally favored, and you've got about the same amount of each. Another way to understand the meaning of the ratio K is to look at it in terms of chemical potential energy, which will soon be called Gibbs free energy. The equilibrium constant K tells you the ratio of products to reactants when a given reaction reaches its lowest free energy state and quote unquote stops. We know it doesn't actually stop because of, dynamic equilibrium. Reactants still turn to products still turn to reactants, but macroscopically, it appears to stop. And this is considered its most stable position. We can actually make a really great analogy between gravitational potential energy and chemical potential energy by graphing the chemical potential energy, or Gibbs free energy, versus the ratio of products to reactants. Just like balls rolling down a hill, your chemical system, wherever it starts off, is going to react or roll until it reaches its most stable position. Of course, the chemical system isn't always at equilibrium. If your chemical system is running, aka the ball is rolling, it means you're somewhere other than equilibrium. For example, if you have too many reactants relative to your number of products, so you're not at equilibrium yet, well, that ball is rolling, the chemical system is reacting, turning reactants into products until equilibrium is reached. And of course, the opposite is true. If you have too many products in your chemical system relative to the amount of reactants and you're not at equilibrium, well, your chemical system is going to turn products into reactants until equilibrium is reached. And that means equilibrium is the lowest free energy, most stable ratio of products to reactants. The thing about equilibrium is the location of that most stable point is different for every different chemical system. So you can have a reaction that is very product favored. That means your ratio of product to reactants, or K, is greater than 1. That means that in your free energy diagram for this product favored reaction, your equilibrium point is going to be at a really high ratio of products to reactants. Well, it can be the other way around too. If the most stable point for a chemical system generally favors reactants, your K value is less than 1, well, this time your free energy diagram is going to show its lowest point, its point of stability, much closer to being pure reactants. And of course, if K is about equal to 1, it's about half and half. That's why it's essential for every given chemical system to make sure you know the value of K for that system. That's how we can predict where a reaction will reach its point of stability. Now, technically speaking, some reactions aren't equilibrium reactions at all. Some reactions actually go to completion. Well, if you recall, completion reactions, where it's just basically reactants go to products and they don't go back, we show that with a one-way arrow. The equilibrium reactions, where they can go in both ways, we show with a double-sided arrow. But you can still look at this free energy diagram as an analogy, because in a completion reaction, it's basically a one-way slope. You're rolling downhill no matter where the chemical system is. If it's not 100% products, that's where it's going to go. That's a completion reaction, and they are non-reversible. You can't go back. Combustion is a classic example. You can't unburn something. Equilibrium reactions, of course, as the double-sided arrow suggests, are reversible, which means the reaction is going to occur until the lowest energy state is reached, and then, who are we kidding? The reaction's still happening, just at equal rates in both directions. So a weak acid dissolution is a classic example. A weak acid will only partially dissolve. So to have a kind of conceptual understanding of K, it can be helpful to think of K as a measurement of how close the reaction goes to 100% completion. If you have a high value of K, the reaction came pretty close to completely turning reactants into products. But low value of K, not so much. The reaction doesn't come close. In fact, the reactants are just mostly hanging around. You'll notice as we try these practice problems, there's a lot of pictures. But honestly, AP loves to do particulate representations. That's the fancy word for the pictures. And it's a great way to visually determine what's going on in equilibrium. So notice they're telling you that all of our differently colored spheres is looking at the reaction of A converting to B and MEC. So A is the striped ball and B is the solid ball. So we want to know which of the three reactions shown above would K be the smallest. So you should go ahead and try this, and when you're ready to check your answer, unpause the video. Well, hopefully you remembered that K being small means more likely anyway that K is less than 1, or it's going to be reactant favored. So we're looking for something that has the greatest possible amount of the reactant, or A. Well, in that case, the one that has the most A is clearly reaction 3. And done. That's all you need to do. 2 more problems, similar idea, different colors. So take a moment and answer these 2 questions. And when you're ready to check your answers, unpause the video. Well, largest value of K should have the most product. So you're looking for the most purple ovaloid things. And the smallest value of K would be the least purple ovaloid things and the most blue circles. That's it. That's all you need to know about equilibrium. So thank you for playing with the glories of equilibrium. The next video will talk about the difference between K and Q.